when you first hear about the dynamic modes of an aircraft, it can sound a little strange, and most people haven't had much experience with this from experience in an aircraft actually experiencing these modes. And so what I'd like to do here is do a demonstration using a simulator. So I wrote this flight simulator years ago, and we're going to use it here for this purpose of demonstrating these modes. And this simulator reads in this input file that contains information about this aircraft. Now, the aircraft that I'm using for this particular example is, I think, nearly identical to the aircraft in Warren Phillips's book that he uses to demonstrate modes of an aircraft. And so in his chapters 8 and 9, he uses the same aircraft basically as he goes through longitudinal and lateral modes. And so I've used, I think this is nearly identical to that aircraft, so we're going to get very similar modes and similar behavior out of this aircraft as he shows in that book. So, and this is kind of nice because these properties are probably closer to manned aircraft type properties that you would see on a real manned aircraft, So the glider example that we've been using up to this point, I actually tried to put it into this simulator and had some issues with it, and so I just went back to this other design that I've studied in the past. So anyway, here's the information. We've got a whole bunch of the aerodynamic derivatives and mass properties and information about those reference conditions and things. And anyway, we're just going to go ahead and run this in the sim and see how this behaves. So okay, so here's that simulator, and the simulator has two different ways we can view things. So this screen here is really nice because it's got all this information numerically. So we're going to use that most of the time, actually. You can also switch over to this view to be more like a heads-up display cockpit type of thing, but we're going to spend most of our time here. So what I'm going to do first is put in an elevator wrap. Now, when in flight testing, this is a very common maneuver where they basically hit the stick with their hand. So I'm just going to kind of put the step input in with the elevator. I'm going to pull back sharply and let go sharply, more of like a whack. I'm just going to hit the stick, and then it's going to excite our longitudinal modes, and I'm going to try not to excite any lateral modes here. So let's see how this goes. Okay, so you can see the aircraft pitch up sharply, and the stick is back at 0, by the way. I just hit it quickly, and so we saw the aircraft pitch up, and now long term it's going to go into a phugoid mode. We're going to be able to plot this afterwards. It's recording this data as a function of time, and so we're going to be able to go back and plot this and look at the mode in a little bit more detail. So we'll just let this run for a second. You can notice a few things. So angle of attack is changing, really small numbers though. This is in degrees, so the angle of attack is oscillating, but not significantly. The altitude is oscillating rather significantly. We started off at 1,000 feet. You can see we're going up to, now we're up to about 15 feet over that. And then it's going to drop down below that again. Our elevation angle, so this is the angle that our nose is making relative to the horizon, is oscillating here up and down, and we could also have a pitch rate that is oscillating. Okay, so let's get out of this, and it records it to this text file. I'm going to take the data in here and drop it into Excel. Okay, and then I'm just going to plot some of this data as a function of runtime, and look at what this looked like as a function of time. Okay, so we started off in this trim condition, and then I did that, it's called a pitch wrap, where I hit the elevator, and you can see as I plot velocity as a function of time that we've got this oscillatory mode here, and this is the phugoid, right? So this is large changes in velocity and only small changes in angle of attack. We'll look at that in just a minute. And in a later video, I'm going to talk about how you can actually pull off the frequency and damping of this mode from experimental data. So this is the type of experimental data that we would have coming down from an autopilot or some kind of system on board the aircraft. So after they do flight testing, then you'd get all of this information dumped in as a function of time. So when I worked at Scaled Composites, this is some of the stuff that I did. Is I took this flight test data and tried to extract different modes. Actually, I was trying to pull out structural modes, so the frequencies that the actual aircraft was vibrating at, not these rigid body dynamic modes. So, but anyway, the process is very similar. So, anyway, I'll do that in a future video to show you how to extract information out of this. But you can already estimate a few things. We can see that this is convergent because each oscillation is getting smaller in amplitude. And so, if you were to connect the peaks here, you'd see this convergent property here of the phugoid. We could also estimate what the period is, based off of the time between two peaks. And that's pretty consistent. And then we could also estimate, the 99% damping time when 99% of this first amplitude is damped out. So, okay, let's look at some other properties here. So now let's look at angle of attack as a function of time. So, and I'm actually going to zoom in on this. This first bit of data wasn't very helpful because, so let's go up to 50 seconds here because we just sat there in trim for a while. And okay, so you can see we've got this huge change in angle of attack right up front. And I'm actually going to zoom on this just a little bit more. Let's just go to 60. Okay, so this rapid change in angle of attack, remember I put in a near step change in elevator. So it took less than a second, and really less than a fraction of a second for me to whack that elevator and have it return back to zero. And so we're really getting some step change right in here, but it excites this response in pitch or in angle of attack. And this is the short period mode. So you can see it's heavily damped. We're only going to get a couple oscillations here before that's all damped out. And it's fairly high frequency, right? So so we're getting, if we measure the time between peaks, so here's roughly a peak and here's roughly a peak. So from about 53 and a half to 55 and almost 56. So we're talking about 2 second period there, right? And 99% damping time, probably 2.5 seconds or something by the time that's completely damped out. So again, this is the short period mode. This is what we experience when we hit a gust or turbulence. It's this high frequency response of the aircraft in pitch, and we can actually plot. Let's see, theta. So that's our elevation angle. We're going to see something similar there. So we get this bump in elevation angle. And then let me reset these axes here so we're running out to the end of our data. So you can see in theta, when we look at theta as a function of time, we see that short period mode and we see the longer term oscillations of the phugoid. Now let's go back to alpha for just a second here. Alpha also, you can see a real slight phugoid mode in there. And again, that's expected. You don't have very small changes in angle of attack, but compared to the short period, these changes in angle of attack are really, really small. So again, the phugoid is mostly a change in velocity. The angle of attack actually doesn't change much during the phugoid. Okay, so these are our longitudinal modes. I'm just going to label this sheet here, longitudinal. And if we were to plot any of the lateral things, so for example, beta was exactly 0 through this whole time. So exciting the longitudinal modes did not excite lateral modes. And that's because we're dealing with a perfectly symmetric aircraft here. And so, if we do longitudinal input, we get longitudinal output. And it's really a two-dimensional problem. So now let's go back and look at some lateral input to this simulator. Okay, so we're going to restart the sim, and this time we're going to look at each of these modes a little differently, but let's do what's called a rudder wrap. So in this case, the pilot would just kick one of the rudder pedals really quickly and then take his feet back off them. And so I'm just going to try to simulate that by doing a quick rudder input and release. Okay, so you can see that oscillation in there, and of course that's the Dutch roll. So our nose oscillated. It felt kind of like we were fishtailing for a second. So that was this Dutch roll. And then this particular aircraft has a convergent spiral mode. And so we can let this run for a minute and watch the properties of the aircraft here. But let's look at, for example, the bank angle. You can see that the bank angle is decreasing slowly back to zero. It's actually, this aircraft is actually leveling out. Um, and that's because it's got a convergent spiral mode. So it's eventually going to return back to level flight as that bank angle goes to zero. Okay, so we've probably run that long enough here. Let's go and look at some of the data. So pull up this and again, copy that into Excel and start a new sheet here. Drop the data in there, and this is our, we're going to be looking here at Dutch roll. Okay, so again, I'm plotting this data as a function of time. We're going to come back to velocity because that's kind of interesting, and instead let's start off by looking at a lateral property like beta. So this is our side slip angle, and you can see from that rudder kick we had this kind of high frequency response of the aircraft. That's the Dutch roll, and again we can see that that's convergent. You know, the peaks are getting smaller as time goes on. Again, this was a step change, you know, right about this time point here, and so we could zoom in on this and extract some information here. So if we started at 15 and went to about 30, we can zoom in on that. So that's the Dutch roll mode, and we could estimate again the period, the damping, the frequency, all those types of things we could estimate off of this data. And this is again the type of data that you'd get from flight testing, where you'd want to then be backing out this information from the actual response of the aircraft and comparing that to your aerodynamic predictions, you know, of how that was going to behave. So, okay, so there's beta. Can also look at the bank angle. So this is phi, and again, the phi is going to pick up that Dutch roll mode. And let's zoom this back out. So we're looking at all of that data, and so phi started off really sensitive to showing us the Dutch roll mode. But then this portion of phi actually shows us the spiral mode. You can see that the spiral mode is convergent, and it's returning to a zero bank angle, right? So as time goes on, this is asymptotically approaching that zero bank angle. Okay, so so here we've looked at Dutch roll and also spiral, and another thing that's interesting that I mentioned earlier is that we can come back and look at some longitudinal information like velocity. Well, the velocity is actually still showing us this phugoid. So if we just plot the velocity as a function of time, you know, there's some stuff up front here. We're getting a little, maybe a little bit of that Dutch roll in there that's affecting this, or that may also be the short period. I'd have to study that a little bit more to figure out which one's going on there. But overall, the velocity is really showing us again this phugoid. So what we learned from this is that when we put a lateral input to the aircraft, it excites not only the lateral modes, but it also excites the longitudinal modes. And in fact, we can see angle of attack. You can see that short period mode happening there. And then, anyway, that may all be short period. I'd have to look at the frequency of that compared to the Dutch roll. I think that's all short period in there. So we're exciting these other modes, the longitudinal modes, even though we were only trying to excite the lateral modes. So, so this shows that lateral modes are a full 6 degree of freedom response of the aircraft. You know, you can't just look at lateral modes all by themselves. You're always going to excite the longitudinal modes, where with the longitudinal modes, we could excite them without exciting any of the lateral modes. And anyway, that's just kind of one of the things that you deal with when you're looking at the lateral modes that you don't have to deal with when you're specifically looking at the longitudinal. Okay, so we looked at Dutch roll, and let's do actually one more thing with the spiral mode. So I'm going to come back in here to this input file. The spiral mode is kind of this trade-off between yaw stability and roll stability. And so I'm going to look at, here's my yaw stability derivative, Cn beta, and that's positive. I'm going to make that more positive so that the aircraft is stronger in yaw stability, and I'm not going to touch the roll stability. CL beta is the roll stability derivative. I'm just going to strengthen the yaw stability by roughly doubling it. I'm just going to put a 1 right there and save that. And now let's rerun the sim. And we're going to try to repeat the same thing as we did last time. I'm just going to put in a rudder kick really quickly. And we're just going to watch the response of the aircraft. So you can see that the Dutch roll was a little bit less fluid. It was a bit more stiff. That's because we increased the spring constant about the yaw axis, basically, this yaw stability. And now the Dutch roll has damped out, but what's happening to the bank angle? The bank angle, instead of converging back to 0, is diverging away from 0. So the bank angle is actually increasing, and it will continue to increase. We're now into a divergent spiral mode. You can see the side slip is increasing. Our airspeed is going to slowly increase. We started off at 180, and it's now going to increase as that spiral tightens, and we keep increasing our bank angle and nosing down into the spiral. So one thing to notice over here is the G-force that the aircraft is experiencing. So the normal G-force is usually right around 1 G. Well, you can see that the normal G's really haven't changed. And this is part of the danger of the spiral mode, if it's a divergent spiral mode, is that the pilot isn't really going to feel this. So there's a small side force on the aircraft or on the pilot. So, he's feeling a very, very small side force, but not something that was really noticeable, most likely, and actually also something very small. So really it's this normal force. He really can't tell that anything's going on. And so if he were in a cloud and didn't have instruments, he could now fly out of that cloud and be completely disoriented, not having felt at all that the aircraft was doing something odd. Okay, let's look at our yaw rate. Our yaw rate continues to increase. So this is degrees per second, and that's just going to continue to increase. Our roll rate is also increasing, although rather slowly here. So you can see that we're rolling to the left, and so that's why it's negative, but the magnitude here is increasing. So now we're up to a bank angle of almost 25 degrees. And like I said, we're in this divergent spiral mode that will just continue unless the pilot does something. So again, the spiral mode isn't terribly dangerous as long as the pilot can see what's happening out the window or has instrumentation that's telling him what's happening. It kind of feels like the alignment is out on his, in the car on the freeway or something, and he just needs to correct for that. So it's really simple to correct. It's really only dangerous when the pilot loses a sense of what is actually going on with the aircraft because he can't feel it. Okay, so let's look at this data now. I'm going to copy that and drop it in here. And this is our divergent spiral mode. Remember, the original version of this aircraft had a convergent spiral mode, and we changed one parameter so that it would now have a divergent spiral mode. So let's look at what happens here. Okay, so let's start with velocity. At first, this frequency that we see in velocity is actually the phugoid again from this disturbance. Again, a lateral disturbance will also excite the longitudinal modes, so that's what we're seeing here in velocity. But then you can see that when that kind of damps out, the velocity just continues to increase, and that's because we are tightening into that spiral. We're catching speed and or picking up speed as we continue to nosedive. Okay, let's look at beta. So beta, we're going to see the Dutch roll mode here that damped out rather quickly. But then you can see that beta is now diverging. Now, beta is still really quite small, less than a degree after all that time that we spent So beta isn't very significant, but it is diverging, and that's because we've got a divergent spiral mode. Here's our bank angle. So of course we have the Dutch roll mode that picked up first. We can see that there, and then we have this divergent bank angle where we continue to increase as the spiral tightens. Okay, and then one more thing, let's look at altitude. That's kind of interesting. So at first we had the phugoid mode that we could see there. That's, this oscillation in altitude. But then as we began to bank and the spiral mode became more prominent, you can see that we continue to drop in altitude as we pick up speed, right? So velocity increased as we dropped in altitude. Okay, so that's an example of a divergent spiral mode. Now, let's look at one more thing here. I'm going to put this, let's see. I didn't realize I had opened multiple versions of this. Let me just close these real quick. So I'm working on the correct one. And I'm going to put that CN beta back to 0.7. So we're going to have a convergent spiral mode again. And now we're going to look at the roll mode. The roll mode is one of the trickier things to pull out of experimental data. So we're just going to take a minute and look at that. Okay, so we've got our CN beta set back. Save that, and let's start the simulator again. Okay, so to excite the roll mode, what I'm going to do is put it in step aileron change, okay? And I'm actually going to hold it for just a second. So I'm going to hold the aileron to the right for just a second and then return it, or actually it's probably going to go to the left here and then return it back to neutral. But I'm just going to hold it out there for a second, then bring it back. Ready? So here we go. Okay, so that's actually long enough to pull out the roll mode. Let's pull out the, get this information, and we'll get another spreadsheet here. We'll drop it in, and this is the roll mode. Okay, so let's look at our properties of the function of time. And okay, so we were sitting in trim for a bit, and then this is obviously where the action's happening over here. Let's look at where we're going to see this is in our bank angle, phi. Okay, so now phi is our bank angle, and the roll mode is really a measure of how rapidly we approach a steady state roll given some disturbance in roll. And so what I used to disturb the roll was I deflected the ailerons. And so what we want to measure here is how rapidly do we approach a steady state rotation rate or roll rate, okay? So I'm going to approximate. So phi is a little bit confusing to look at. Let me zoom in on this though really quickly. So let's see, we started that at about 19 seconds. And let's actually go 19.5 and really zoom in on this. And then we're actually going to come up here to about 22. That should do it. Okay, so what we're trying to measure here is how rapidly do we approach a steady change in roll rate. So that would be when this line hits a constant slope. So we're trying to look at how quickly do we change from 0 to something that has constant slope. So the way I'm going to do that is I'm going to approximate my roll rate. Now, unfortunately, I just didn't have the sim set up to spit out the roll rate. The roll rate is actually something very easily that you can get from gyros or instrumentation on the aircraft. So actually, you would usually have roll rate, but we're just going to approximate it here. The approximate roll rate, and we're going to say that it's equal to the change in phi. So the derivative of my bank angle, the change in phi with respect to time. So I'm going to just do a finite difference here to approximate that roll rate. And now let's look at that as a function of time. Okay, so this kind of paints a different picture here. And this is a little bit more what we're expecting. So we had some step change in aileron, and it wasn't a perfect step change because it took me some time to get the aileron over there. So this corner isn't maybe quite as sharp as it could be. That depends on how quickly I can get the aileron over there. But basically, I got it over there rather quickly and then held it there. And you can see that our roll rate was originally 0, and then we increased our roll rate, or really decreased because we were rolling to the left, but we increased that and asymptotically approached some constant roll rate. And then I moved it back. So that's what this step change is here. So then I let it go back to 0. And again, we came back and asymptotically approached a constant roll rate here. So it's a very convergent mode, extremely highly damped, very, very much over damped. We're not going to get any oscillation in here. Really what we're looking at is how much time does it take for me when I have a disturbance in roll to get up to a constant roll rate. And so we could estimate the 99% damping time in here. I'd probably have to fly this a few times, and maybe I could clean up this data just a little bit and get better at putting in a step aileron change. But basically from this data, we can estimate how long it's going to take for this roll mode to dampen out and to hit a constant roll rate. Now you can see the times on these are really quite small. So we're talking about maybe a half a second, maybe a little bit more than that, until this thing is completely damped out. And so that's why pilots associate a change in aileron deflection. If they deflect the ailerons, they associate that with a constant rolling rate. To them, it almost feels instantaneous. When they deflect the ailerons, they begin rolling at a constant rolling rate. And they don't notice this transient because it's so short and it's so heavily damped. So if we go back to phi here, really what they feel is this constant change in the bank angle given some aileron deflection. If they want the bank to be changing faster, then they increase the aileron deflection, right? Or if they want it to be slower, they decrease it, and they feel like it's almost this one-to-one. And what they're not experiencing, or what they're really not noticing, is this transient right here, which is the roll mode, which is the time it takes us from the time they deflect it, the time it takes us to get up to a constant rolling rate, or a steady change in our bank angle, so roughly. So anyway, that's the roll mode. And usually, the roll mode isn't really a problem on most aircraft. Now, when I worked at Scaled, I worked on the Stratolaunch aircraft, and that aircraft we were concerned about the roll mode, and that's because it had so much inertia about the x-axis. We wanted to make sure that the ailerons were large enough so that when the pilot deflected the ailerons, the aircraft responded rapidly, or at least rapidly enough for that pilot to maintain control of the aircraft. And so our transients were much longer because it took a while for that aircraft to ramp up to a steady rolling rate compared to a smaller aircraft, that would ramp up to that much more quickly because they don't have nearly as much inertia about the x-axis. So, okay, so this has been our overview using a flight simulator to kind of study these different modes, and hopefully just seeing that from the cockpit view, so to speak, is helpful in understanding what each of these modes is, and also how you could use experimental data from flight testing to estimate the dynamic modes of an aircraft.